first of all, let's do C2, 6. AL203. Do you know the difference between these and these? That's review. These go in a category, these go in a different category. Do you remember? Yes. These are ionic compounds. You know that because these contain all nonmetals, and these contain some nonmetal and some metals. That's ionic versus covalent. We haven't studied these yet, so don't worry about it. If these seem weird compared to these, I bet they all seem weird. But there's this thing about formula unit, also called molar mass, that I think it's worth showing you. Oh, I didn't bring any here out of tables. All right, I'll do it as we go. But yeah, I shouldn't start there. I'll come back to formula unit. So those of you who have taken chemistry before, you remember the moles. Does anybody have a periodic table? Oh, you know what? There's one in the back of this thing. I didn't bring all my periodic tables. Okay. If I said I have, well, first look at oxygen. Symbol O on the right side near the top. Do you see the number? That is sometimes called AMU when we're talking about isotopes, but most of the time what we mean is 15.999 grams per mole. And that's the number we use most of the time from the periodic table. All right, this relationship, though I would say do it like this. Okay, notice there's almost always a number, a unit, and some kind of label. So let's talk about oxygen atoms. Let's just say we have oxygen atoms. If I did that, I would put in parentheses out here. Parentheses. Now we have a numerical value, a unit, and what I call a label. So how many moles of oxygen? 6.022 times 10 to the 23rd oxygen. Let me put it like this. Oxygen, unit, numerical value, unit, label. And then if I said, two different things here. And let's say I had 2.36 grams of oxygen. Three different ways I might refer to oxygen atoms. what you need to notice here is that this, when there's no unit here, actually means something. So let me put it like this, and I'll do this. 1 dozen equals 12. If I wanted to do oxygen atoms, I would have a label. But again, notice numerical value, unit, label, but this doesn't have a unit. And I want you to notice that because it'll help you decipher questions. When you need to use this number and when you don't. This huge number is just a standard number. It's actually an integer. It's just a gigantic number. I could go 1, 2, 3, 4, 5, 6, 7, 8, all the way out to 23, and I just have a bunch of zeros, but it's an integer, it's still a huge number.
I don't know if I'm like, with Avogadro's number, can you use that to convert with any, like, unit? Like grams, milliliters,
There is a relationship to it, but what I would say, the thing that you can do anything with, it doesn't have to be oxygen atoms. It could be pencils on Earth, grains of sand on a beach, stars in the sky, things like that. We would use this. Dozen we use for very, very simple numbers, but something that's huge, we use this. Astronomers sometimes use this, talking about numbers of stars. I don't know if anybody goes around measuring grains of sand on a beach, but those are just problems you could use for this huge number. But what I'm trying to say is this and this are really exactly the same thing. I call them counting units. 1 dozen equals 12. 1 score equals 20. 1 pair equals 2. And 1 mole equals 6.0. Let me write it out. 022, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. These things are literally the same idea.
Oh, okay.
You follow that?
Yes.
This is just a huge number. There's several reasons why it's confusing. We almost always use powers of 10, that is scientific notation to write it. Another reason it's confusing, it's a huge number and it's just mind-boggling. But realize it really is the same as this. So let me say, if I asked you to walk out in the parking lot out there and count the cars, if I just said, go out there and count the cars, and let's say there are 18 cars out there, you'd walk out there and count them and come back and say 18. That's because it said how many cars. If I had said how many dozen cars, you come back and say 1.5. 18 is 1.5 dozen. And notice when I said count how many cars, there's no unit. I didn't mention a unit. I just said go count the cars. If I said dozen, then you come back with dozen. If I said, then you know you're dealing in this number. If I said score, you'd be dealing in this number. If I said pair, this number. And I wouldn't say mole to count cars, but it's the same idea that 1 dozen something is 12 blank something. One score of something is 20 blank something, that is 20 something. The point is, let me set up that dozen problem. I think I can make it a little more obvious. And that's what I was doing over here. 1 mole of oxygen, this many number blank oxygen, 2.36 grams oxygen. This is missing a unit. And that's what I'm telling you to look for. It just means when there's no unit, that just means, you know, when you were in 7th grade, your teacher asked you to count something, you would just count like that, whatever you would count. To do this. You go out there and you count that there are 18 no unit cars. And on the way back, you go, oh, he asked me to give him this in dozen. 1 dozen, and I'll say cars, equals 12 blank cars. I'm going to use that to solve this. 1 dozen cars, and I'll put down here 12 blank cars. Or I'm going to use it this way, 12 blank cars on top, and 1 dozen cars on the bottom. So this is just this flipped over. If you want the units to cancel, you're looking for blank cars to be down here. Which means we're using this one, and I put 12. 1 dozen cars is 12. 1 dozen cars equals 12 cars. There's no unit. So that's how you would set it up. All right. And if I said moles, if I sent you off to count something, or no, let me do this the other way. This equals 1.5. The unit always goes with the label, even if it's a blank. So that cancels that, and we end up in. So that's one way you might get this problem. The other way around is you're not given a number. You're given it in dozens, and you have to find just the number. So let's say I went out there and said there were, let's say there were 30. That's let's say I went out to a different parking lot, and I came back and said there are 2.5 dozen cars in that parking lot. How many is that in just cars? You're still going to use this relationship to dozens, but now you're going to use it flipped over, where you're going to have 1 dozen on the bottom and 12 cars on top. Now, if you calculate that out, dozen cars cancels with dozen cars. If I did this right, 24 plus 6, yeah, that's 30, right? So this times this, we end up in 30 blank. I went out and counted it, there were 2.5 dozen. And I came back in here and said, tell me what that is in just numbers. That's how you would set it up, and you would find that 2.5 dozen is 30 cars. Of course, this is the most formal way to do it. If you're sitting there doing it in your head, it's a slicker way, a shorter way. It's probably the same one. I just like to do it really explicitly like this. All right, now I'm going to do moles, and it ends up exactly the same way. Let me move this over a little. 30. So 2 different ways you can deal with these. All right, now we'll do something in mole. I don't have to use really large numbers now. But let's say we have, you're reading a question and it says you have 2.56 times 10 to the 20. I'll say oxygen atoms. I'll just say O. A question asks you, have that many of these, how many, place from a numerical value. So it's, it's oxygen atoms. So a question would say something like, I have this many oxygen atoms. And you'll notice when you read the sentence, there's no unit. So that clues you in. And then you will go 1 mole of oxygen atoms. And now the numerical value here is 6.022 times 10 to the 23 blank oxygen atoms. So ultimately what you're doing now is dividing this by this. The math would be, the way I would do it is I would do 2.56 divided by 6.022. And this is 10 to the 20 on top, and on bottom, 10 to the 23. This I'll do in my calculator, 2.56. And you get your significant figures there too. 2.56 divided by 6.022 Calculator says 0.4251079, et cetera, but I'm going to stop at three significant figures. So 0.425 times 10 to the what? I take 10 to the 23 to the top, which makes it minus 23. And now it's 20 minus 23 gives me 10 to the negative 3, which is 10 to the negative 3. That would be the answer. Or I would probably want to go blank, oxygen atoms. That would be the answer to this one. And that's the analog to this one. It's some number blank the thing we're counting. Some number blank the thing we're counting. And then the relationship. 1 dozen things is 12 things. 1 mole things is this many things. The blank. This blank oxygen atoms cancel. You're left with moles of oxygen, which is what I have here. And 0.425 times 10 to the negative 3 is what would be here. Scientific notation would be 4.25 times 10 to the negative 4. That's the scientific notation. But if you're not asked for standard scientific notation, you don't need it. So this one is the analog to this one. Guess I could write this in. 0.425 times 10 to the negative 3 oxygen atoms. And again, there's a blank there where you would generally see a unit. And then the analog to that do it like this. So now when someone walks up here and says you have, I'll do 2.919 moles of oxygen atoms. How many oxygen atoms is there? It's like saying I got this many dozen cars. How many cars is there? This is saying I have this many moles of oxygen. How many oxygen atoms is that? And it's going to be a huge number because 6.022 times 10 to the 23rd is now going to be on top. So I'm using this but flipped over so that moles cancels. 6.022 times 10 to the 23 oxygen atoms is 1 mole of oxygen atoms. Again, I'm just going to multiply this by this and hold on to the 10 to the 23. It won't show up in scientific notation, I don't think. So 2.919 times 6.022. Calculator says 17.58. 4 significant figures. 5, 8. And then I'm going to tack on the 10 to the 23. 23. 23. And that's it. The moles canceling, we end up with ... oxygen atoms. So this equals 17.58, 10 to the 23. Oh, this was mole. My bad. That was mole, not ... So I think if you wrote these down in your notes, this and then this as the analogs to each other, you'll at least get a bit of a conceptual idea of what's going on. It really isn't any more complicated than working in dozens or pairs or whatever. What bothers you is A, the power of 10, that just messes with your head. The fact that it's a huge number makes it kind of hard to think around. It's related to chemistry, you got all these other concepts going on. You might just now be learning how to do these calculations properly. But there's a lot of reasons why students find the mole confusing. But the best way for me to explain it is that it's a counting unit, just like dozen, just like score, just like pair. It's just a huge number, and you've got a power 10 to deal with. And you generally have to be able to read a question and decide which way you're using this. But one mole is 6.822 times 10 to the 23rd. That's the relationship. Just like 1 dozen is 12. You guys with me? Let me point you to something in the book for practice. I admitted earlier I'm behind on putting questions up. Some stuff from last lecture still I don't have questions up. But if you can do the problems that are on D2L, then you're ready for the test. So that's how you keep up. Things are a little amorphous right now because we haven't seen y'all since last Wednesday. So it's kind of like you forget everything you're doing. But in the book, in chapter 4, at the end of chapter 4 in the exercises, they give you the odd numbers, so 79. Let's see, calculate the number of moles. Okay. Calculate the mass in grams. Okay. Calculate the mass in grams. Okay, 8788. And the other way around, these are asking for, no, that's asking for moles. I mean grams. I will get practice problems like those. Never mind. I will get practice problems up. Just have that in your notes. Let me do one more thing and then we'll do lab. Back to where I tried to start. Covalent compounds and ionic compounds. First of all, look at oxygen again on the periodic table. Oxygen. You see that number. Think of that as grams per mole. You can also think of it as, I'll say number of oxygen atoms. .02 times 10 to the 23rd oxygen atoms is 15.999 grams oxygen atoms. And this means 15.999 grams of oxygen atoms is 1 mole of oxygen atoms. Same thing as saying this many oxygen atoms weighs 15.999 grams. But this time I'm going to focus here. and we'll talk about grams to moles. So we're actually going to leave this number behind. You use this number when you get a problem that says so-and-so and so blank finger on it. That's what I was pointing it out. It helps you point those out. But I will get problems up and we'll review them. I'm still half a click behind with lecture. All right. So a question like that. I've got 2.68 grams of oxygen. How many moles is that? You get that number off the periodic table, you set it up like that with your label, and you realize you might use it like this. I'm using the number for oxygen off of the periodic table in the back of your lab. What you probably see on the periodic table I gave you probably says 16. That one's just rounded to four significant figures, while this other one has 5. Right? My periodic table has 16.00.
Yes, sir.
It's fine to use that. This is just slightly more precise. Actually, let me just do that. I'll write it as 16. 16.00 grams of oxygen atoms is 1 mole of oxygen. All right, we're given grams, so we need the one that has grams on the bottom, so we're going to need that one. 2.68 grams of oxygen atoms. And then we're going to go 16.00 grams of oxygen atoms on the bottom. And that's how we solve it. Um, 2.68 divided by 16.
Could you put the camera on the board?
Thank you.
Thank you.
Okay, so I'm solving this problem. This is how to set it up. 2.68 divided by 16. 4 significant figures, 3. My calculus later says 0.1675, but I'm going to do 0.168. Grams of oxygen cancel, grams of oxygen cancel. We're left with moles of oxygen. That's how you solve this. The other way around, just like before, there's another way to solve it when you use this flipped over. That's when you're given moles and you're asked for grams. So if I say, here's a different problem. And do notice, there's no missing units. There's no blank ... theme, no label. Let's see. Let's see, I had, whatever, we'll do 2.68 now. No, that's confusing. 4.14 moles of oxygen. How many grams? How many grams of oxygen is that? This time, I'm going to put the number here, 4.14 moles of oxygen over 1. And now I'm going to flip this over. 16.00 grams goes on top, and the 1 mole goes on the bottom. So either you're given grams and you find the moles, or you're given the moles and you find grams. If I did this in my calculator, I would do 4.14 times 16, 66.24. Moles cancel or the grams. And that's the answer to that problem. 3 significant figures, 4. All right, I'll leave that brief like that. I will review this once I get the questions up. But these do have practice problems. Remind me to go back to the camera. Actually, we're about done, but. Nope, one more thing. Where I tried to start today. This is also called unit mass, also called molar mass, and a few other near synonyms. But just look at it like this. What I had up before, C2H6, C2H6O, I think I did SF6. I had CaCO2. Remember what I had here? Okay, so what's the difference between these two? These and these. These are ionic compounds, which we've begun to study. These are covalent compounds that we haven't studied, but these are the formulas for these compounds. Slightly different words are sometimes used for ionic versus covalent, but just think of it as formula mass, and these are the formulas. Formula being the ingredients in a particular compound. All right. Formula mass is this. For this one, I have aluminum. There are 2 of them. I have oxygen. There are 3 of them. Now look on your periodic table for aluminum and tell me what that molar mass is. Say it loud. 96.98.
26.
Say again.
26.
26.
Yes.
And oxygen is 16. Okay. I want my calculator. So if I do the math here, 2 times 26, 98. In this case, I'm going to keep all the digits, or at least a lot of them. 3 times 16, 48. Now I'm going to add them up. 6, 3, that's 107 grams per mole, or 107.36 grams. Al2O3 is 1 mole. We did all of that just to get that relationship. If we were just dealing in aluminum atoms, we would just look at the periodic table and we'd get the grams per mole from there. But when you've got a compound, you've got to add up everything that's there, and then this is the grams per mole for this compound. So you can solve problems like, if I had 2.63 grams of aluminum oxide, how many moles do I have? And then you could solve this. Or I could say, I have this many moles of aluminum oxide. How many grams is that? Then you would use it, how many moles? Then you would use it like this. You see what I'm saying? It's the same idea, but now we've got compounds we're dealing with, not just individual atoms. But you go through this process to find the grams per mole, rather than just look at the periodic table the way you do for atoms. And then you can use that in those same types of problems. And even though we haven't studied these yet, I wanted to bring it up because it works exactly the same way. C2H6, carbon, I have 2 of them. Hydrogen, I have 6 of them. Carbon is 12.01. Hydrogen is 1.01. This will be 24.02. This will be 6.06. Same idea, 30.08 grams of C2H6 is 1 mole of C2H6. And again, you can use those in those types of problems. Most of the time when we're working with grams in here, when we're working with moles, it's literally this, it's grams per mole. However many moles you need, you can walk in a lab, measure that many grams, you know how many you have. Because painstakingly chemists, scientists over the years have made the periodic table that tells you these values that are so important. So we can find numbers of moles just by weighing things on the scale. Does that make sense? Okay, I'll stop there. Let me introduce the lab to you.